first lab we usually do with lenses is with a converging lens. And what we do is we have a bright object, in this case a candle. We put it a certain distance from the lens, and then we look for where a real image forms. You can find that pretty easily if you take a note card. The note card, if it's in the location of the real image, you'll see it in focus on the screen. We use what's called a meter stick optical bench that lets us easily move these different components around. So there's a couple of things to notice. The first is that the real image is inverted. And the second is that it's a different size than the actual candle. So all of these things are related to each other, as well as to where the location of the image is. The purpose of this lab is to discover the rules that govern that. What I usually have students do is take a selfie and then use that selfie as the object. If they turn the brightness way up on their phone, you could actually make an image on a note card using one of these lenses. And the independent variable, the one that we change, is the object. We move it different locations from this lens, and then an image forms in different places. So I think that's the easiest way to see this. When I move the phone different places, the image shows up in different places. Because of COVID, I did it a little bit different in 2020, 2021. We weren't allowed to share lab equipment, which meant we couldn't really be moving the screens around. So I did it backwards. I set up 5 of these benches around the room. I put the lens and I put the card at a fixed distance from the lens. So in other words, I was determining what the image distance was. Then I had students take their phone and their selfie and move it to the right place to make an image on that screen. So it's kind of backwards. So the object distance, which usually would be the thing we changed, gets labeled SO for distance object. S is traditional here. The note card is the image, so SI for image distance. Now, we need to sort of ask ourselves, is there any way geometrically we can see ahead of time on where this image is going to form? One way to do that is with what are known as the principal rays. Every point along this object is sending light out at lots of different angles, which are being collected by the lens to make the image. But there's 3 of them that are easy to figure out where they come back together. And the easiest to understand is what's known as the central ray. So if I have a line leaving the head of this guy and passing right through the middle of the lens, the head of my image is going to be on that line. The reason this is not deflected, it's not easy to see in this sketch, but in a real lens, this light would be hitting the surfaces perpendicular, so it would not bend according to Snell's law. That doesn't determine where this is. This could be anywhere along this line. In order to get an idea of where the image is, we need to know something else about the lens. A converging lens is going to take parallel beams of light, and it's going to bend them and make them all pass through a point, which is known as the focal point. So different curvature on the lens is going to shift this focal point around, and that's going to be really important for us in figuring out where the image distance is for any given object. Let's see why. So let's send a parallel beam of light, so parallel to the central axis, from the head of my object. Now, we know, of course, that since it's leaving the head of my object, it's going to hit the head of my image. So I'll make that connection. But notice it's passing through the center here. it's being deflected to a point right here. And that's actually the focal point of this lens. Any other parallel beam of light would be deflected through that point. So it's not that for any given object distance, the image ends up at the focal point. But because the parallel ray bends through the focal point, the fact that the image is in this case right here, it tells us that the focal point must be here. So as we shift the object around, the image is going to shift around, but this ray is always going to continue to pass through the focal point. Notice that these two are converging on the opposite side of the central axis. That's what really helps me justify the fact this image is inverted. Also notice it's a different size than the object. One final thing, these two, the parallel ray and the central ray, can help you find an image. You feel much better if you have a third one. And the third one is what's known as the focal ray. So I'm going to draw the focal point just as far on this side as this one is on that side. I'm going to draw a third ray that leaves the head and hits the lens after passing through the focal point. This is kind of the opposite of the parallel ray. And the lens bends this one parallel. And as you can see, it converges right there on the image like we'd expect. So I am claiming there is a relationship between SO, SI, and the focal length. People have studied optics for a long time, and the equation that they've come up with is known as the thin lens equation. It looks something like this. 1 over the object distance plus 1 over the image distance equals 1 over the focal length. So what we're going to do is look at data for lots of different object distances, look at the image that they form, look at those data, and we're going to try to see if this equation holds true for a range of values. So here's the data we ended up with as a class. Although doing it this way, I think introduced a lot of confusion, it meant that we did get pretty good data because for all of these image distances I had set beforehand, we were able to average lots of observations of where students had to put their phone to make an image. So I'm pretty confident in these data points. Now, the problem is because we set the image distances and not the object ones, we have a lot of missing data here. Like what would happen if I was to put an object closer than 5 centimeters? Or really anywhere between 10 and 30 centimeters, what would happen? So what we're gonna do now is try to fill in some of those gaps. I'm gonna get some missing data doing the lab the way we usually would, moving the object around and seeing where the image forms. In order to see what I should check, I'm going to sort this data by object. So I'll have the spreadsheet help me with this. Data sort range. I'm going to say sort by column C. And data has a header row. So yeah, it looks like I've just got 5. I don't have anything less than that. And then I've got kind of some random values all the way up to 30. So here's the values I'm planning on checking. I'm going to start with 3 inside that 5. And then I'm going to do kind of the odds, 7. We already had a 9-ish. We already had an 11-ish. So 13, 15, 17, 19, all the way up to about our last observation. It's hard to make a video of this because I'm filming this on my phone and my object is going to be a selfie on the phone. But basically, what we're going to do is place an object 3 centimeters away, and we're going to move that note card around to find the image. So the opposite of what we actually did in class. I'm then going to repeat every 2 centimeters until we get as far away as the farthest measurement we actually did in class. So here's the results I got. And you can see an image distance of 5 is a really big deal. As I started to move my object farther and farther away, where the image was approached 5 and never really changed. So I actually didn't end up getting that many more useful data points. So I went back and put in some of the even centimeter distances from the lens just so I get some more data. And what I'm going to do now is add that to the data table, and we'll see if we can make a useful graph and try to figure out what the relationship is. All right, so here's all the data combined together. We'll sort that by object distance. Again, just to see sort of qualitatively what's going on. And I think we can see that when we're close to 5, we have an image that's really far away. But as we up our object distance, as we move the phone farther away from the lens, the image gets closer and closer to the lens and then peaks at 5. It doesn't go past it. So that 5 is obviously something really, really important, because notice that we get our farthest away image when our object is close to 5. And when we have far away objects, the image forms close to 5. So 5 is probably what the focal length of this lens is. That's probably why we're seeing such things happen. But we'll determine that using the equation. Notice I don't have 3 centimeters on here. I checked 3 centimeters. I couldn't form an image anywhere. So that would imply, if 5 is indeed the focal length, that putting your object inside the focal length of the lens makes it impossible to form a real image. So if this equation does indeed describe the relationship between focal length, object, and image distance, we should be able to linearize it. A, as a check to see whether it's true, and B, a way to find the focal length and see if it is indeed 5. We said the object distance, where I put the phone, is my independent variable, and the dependent variable is the image distance, where I put the note card. So I'm going to get the independent variable by itself. So I just subtracted 1 over SO from both sides. And now I'm going to line that up next to y equals mx plus b. On the y-axis, apparently we ought to have 1 over image distance. On the x-axis, we're going to have 1 over object distance. So what's the slope here? I'm guessing it's just the negative sign. And that means the intercept for this graph ought to be pretty important. We ought to see it being the inverse of focal length. So expecting something like this, where whatever this intercept is 1 over f. Let's check. So a spreadsheet can get us this information very quickly. I'm going to invert all of my image distances by typing a formula in. And the way we can do that is we can type equals. That tells the computer to do a calculation. So I would like to do 1 divided by my image distance. And I can have it do all the image distances by just clicking the first one and hitting enter. And Google Sheets knows that I actually want to do all of these, so I could do the suggested autofill. But on any spreadsheet program, you can get it to do an autofill by highlighting the formula you just took, mousing over the little blue square until your mouse turns into a crosshairs, and then clicking and dragging. So I've now got all of my inverse image distances. I could do the same with my inverse object distances. So equals 1 divided by, here's my first object distance. Now I'll click and drag. How you do this is going to be different in every spreadsheet program. But here's how Google Sheets looked in the spring of 2021. It was really bad at determining what you wanted to graph. So I advise students to pick a cell nowhere near the data and then hit the graph wizard. This gives you a blank graph that you can fill in yourself and not have to mess with. You have to add the y-axis first, which Google Sheets calls series. So we're going to click on Add Series and select Data Range. So I'm just going to click and drag over every one of my observations. Hit OK. Now it's time to add the x-axis in. So we click there. You have to press this extra little window thing. If you don't, it'll drop you out of the program. And now we're going to click and drag over all of our object distances. Okay, so what we have is not super useful yet. We don't really want a column chart or a bar graph. We want a scatter plot. So here's our data. And what I see here is something very linear with two exceptions. First is this data point. This was noted in class that this one didn't seem to fit with the others. One of the students was very bothered by it. And in general, we can't just throw out data, but I think the way we did this lab sort of suggests that there was a problem with this data point. Now, every student who measured it got values about the same amount for where the object distance needed to be. So I don't think it's a measurement problem. But you got to remember the way we did this because of COVID is there was 5 different setups with 5 different lenses. It seemed like the lenses were identical, but I'm guessing this one was different. So I think we can exclude this data point. So I'm going to go to the graph, back to the data, excuse me. And I'm going to look for where that is. And that is this one right here. And I'm going to remove it from the data. Again, I don't think that's dishonest. I think we just had the wrong lens. So the other issue with the data is we appear to kind of reach a plateau here. And we would expect the trend to continue up in this direction, but instead it just kind of ends here. And let's note that that's because basically we're talking about situations where we started to have the objects so far away that our 1 over object distance really dropped. And essentially the image started to approach 5 centimeters, which we suspect is the focal length. So I think probably there's more data here that would connect these points a little better, but we just didn't have the precision to measure exactly where the image was as it got close to 5. So this kind of plateau here, I think is just an artifact of our ability to measure. We should label the axes. Chart title is worthless, takes up space, but horizontal axis title, this is inverse object distance, which is in inverse centimeters. This is inverse image distance. Inverse centimeters. And let's get a best fit line for it. You can do that by going down to series, trend line. And to get its equation, we can change the label from none to use equation. So that's our equation. So kind of what we expected, a value pretty close to -1 here. And this is telling me that 1 over my focal length is 0.247. It's suggesting my focal length is 4.05 centimeters. There was a lot in this lab, and I feel like the way we did it because of COVID probably made it more confusing. So what I hope you got out of it is there's an intimate relationship between where an object is and where its image is. That as we move an object farther away, really towards infinity, its image gets smaller and approaches the focal point. As we move the object closer to the focal point on this side, the image gets farther away and bigger. If we go inside the focal point, we don't see a real image at all. That's not to say we never see an image, and that's something we'll have to talk about in another lesson, but we can't make one on a note card. And I hope you saw that image and object distance is inherently related to focal point using the thin lens equation. If you got that and you enjoyed playing with lenses, then I think it was probably a good use of time.